Hello, everyone. Let's continue with the topic of horn antenna in this lecture. Just to remind you, remember that we had an open uh, ended waveguide antenna earlier. We studied this type of wave antenna, and this, we said the directivity is going to be in the order of 3.5 dB. We needed a little bit more, so we thought, okay, we need to increase the aperture size. So I think this is more realistic. So when you have a waveguide antenna, uh, based on the frequency range that you are working, you know what is the cross section A and B. For example, if I'm working in X band, the waveguide in X band, this is 8 to 12, approximately 8 to 12 gigahertz. The waveguide is WR90, and A is 22.86 millimeter, and B is 10.16 millimeter. Let me double check that, 10.16 millimeter. So essentially, you know the cross section that you have, and based on the previous lecture, we saw that we have about 3.5 dB directivity. Now, if you want to have more directivity, we said we can increase the aperture size by going to the horn antenna. So here I have an open-ended waveguide antenna. So you see the size of the aperture is here. As you learned, A is in the center, frequency is about 2 lambda divided by 3. B is about lambda divided by 3. Now, if you want to change it to horn antenna, here you have the same waveguide here, and then you go to a bigger aperture right here. So as you look at that, you have your waveguide, and then you flare out the aperture, and this is from the A dimension, and this is from the B dimension. So you increase the aperture size. So with this, you're going to get a more directivity. If you want, and like for example, we have this antenna working in the same frequency, but this antenna has a smaller aperture, as you see. So you expect less directivity with this one compared to the bigger horn antenna if they are operating at the same frequency. I mean, when you have a smaller horn, the chances is the horn is operating at higher frequency. But in this case that they are in the same frequency, then you say this has a bigger aperture, so this has more directivity. And in fact, you're going to be testing these two antennas in one of the labs. So, so so we essentially need to increase the aperture size. For example, this would be now the new A, this would be the new B. So that would be your aperture size. Therefore, this would be your horn antenna. So you see, you have a transition from waveguide to a horn. So you go from a smaller aperture to now a bigger aperture. And remember, directivity is 4 pi lambda squared, aperture efficiency times physical aperture. So this is in total your effective aperture. Now, I should say maximum directivity here, because directivity in general can be a function of angle theta and phi. Now you see here with this one, the aperture is limited. Aperture size, physical aperture is this times that. And if you remember, aperture efficiency for waveguide was 81%. So this one for waveguide was about 81%. So you essentially cannot exceed some value of directivity. But if you increase your physical aperture, as long as you can keep the aperture efficiency reasonable, you can increase your directivity. And that's really the topic of horn. And because in this particular horn, we increase the aperture in both directions, this is a pyramidal horn as opposed to E-plane sectoral and H-plane sectoral horn. Now, if we'd like to design this, perhaps what we can do is to look at it at two cross section. For example, one cross section could be, so if this is my X, this is my Y, then this is my Z. So let's look at it from cross section XZ. So XZ cross section, if I look at that, then remember XZ is my H plane. So XZ is my H plane. To show that to you, perhaps I can look at the electric field. So if I look at the electric field, this is my electric field. So you see my electric field is along y, and the direction of propagation z, so yz is E plane and xz is H plane. So I can look at this structure from these two cross section and see what I need to determine to design a pyramidal horn antenna. So let's start by plotting this one in the H plane cross section. So let's do that. So if I do that, then I have this cross section, and then it flares out. So maybe I can remove this. And now what is this? This is my small a. So I'm in the xz plane. So xz, so you're looking right now at this a. This is your a. And then you continue, and then you get to this point, and then after that you get to this point, this aperture from here to here, which is this aperture size here. This is capital A. So this is, let me just emphasize the cross section of the horn. You can also look at it more carefully. This is the XZ cross section. So you go from a small a to capital A. So, and the other thing, I mean, I can have a couple of more things. For example, these two sides, if I continue them, they're gonna be intersecting at this point. I may call this, for example, I may call this distance R1. Then because this is my H plane, I could call this RH. And this distance from here to here, I can call it LH. So you see, I go from a small a to capital A, then if I continue this geometrically, they intersect at this point, and then from this point, I can identify three values, R1, RH, LH. So that would be my XZ cut. So I can also have my coordinates here so that you see this would be my X, and this would be my Z. So this is the horn antenna from this cut. Now let's go to the horn antenna from the other cut. So I'm gonna plot it here. So this time I'm looking from YZ plane. So I'm actually a start from here. So now this would be my starting point, like that. And then it flares out and I get to this point and this point in this cross section. So it flares out like this. And I go from this a small b, which is this point, a small b, flares out, and I get to capital B here. So this is my capital B. And then similar to that, I can continue these two lines, and then they're gonna intersect here. This is, I called R1. Similarly, I'm gonna call this R2. So to be more accurate, this is exactly at the aperture. So I should probably plot it a little bit better. Perpendicular to this line, and here the same thing. This is RE, and similarly this is LE. And E stands for E plane. So if you compare that, they're very similar. This one was in the XZ H plane. This one's going to be in the YZ. So you start from here. So this is essentially Y axis according to this coordinate. So I can just say this was Y and this was Z. So this is the two cross section that I have for my horn antennas. Now, let's see what do we need to determine to design our horn antenna here. So if I want to design the horn antenna, the three-dimensional horn antenna, I need to know the dimensions of the horn in these two cross sections. So let me start with the pieces of information that we usually have. So what do we know usually? What are the pieces of information that we have? So first of all, we usually know what waveguide we are using because we have a waveguide, and this is going to flare out to become our horn antenna. For example, in this case, this waveguide that we have here and this which flare out to become horn is a WR90. As soon as you know your waveguide, you know its dimension. So if you remember in a few lectures before, I actually wrote a few waveguide based on WR rectangular waveguide. So you know the dimension. So if you know your waveguide, you know a small a and a small b. So this is the two pieces of information that you have. So you know these two. The other thing that usually you know is the directivity that you want. So you essentially want some directivity. So and usually this is in the form of maximum directivity. So I call it D naught. So we know the maximum directivity as well. So these are what we already know. Now, what are the unknowns? So if you look at here, you can immediately see your unknowns. So perhaps one of the more important ones is your capital A and capital B, because this is your aperture size essentially. So it's capital A and capital B. That's the aperture size. So these are unknowns. You also have R1 and R2 in terms of geometry to be unknown. You also have RH and RE unknown. You also have LH and LE as your unknown. So in total, you have 1, 2, 3, 4, 5, 6, 7, 8 unknown. So if you know all these unknowns, you can actually fabricate your horn antenna. So this is the situation that we have, and we need to start with the pieces of information and one by one determine the unknowns to finish the design of the horn antenna. Now, to begin the design, let's focus on the directivity. So if we know the directivity, this is going to give us one equation in terms of capital A and capital B, because we know that directivity is 4 pi lambda square aperture efficiency physical area. So this is the maximum directivity. This is the equation that we have for the maximum directivity. And the nice thing here is that we know this is a pyramidal horn antenna. So this is the aperture of the horn. So you have your capital A and capital B. So if you look at the aperture of this horn, the area is A times B. That's the rectangle, right? This is A times B is the area. So physical aperture is A times B, of course. So I can just remove this and write A times B. And now the problem is we don't know aperture efficiency. For horn antenna aperture efficiency, it's reasonable to assume it's about 50%. So if I want to be a little bit more consistent with the book that I'm referencing for this, 51%. So we can assume aperture efficiency for horn is 51%, and I'm going to get back to this in a moment. But if we assume 51%, that actually make it very nice, and I'm just going to write it here so that we can have it here. So D naught is 4 pi lambda squared aperture efficiency 51% times the physical area AB. Now look at this equation. This equation is actually very helpful because it connects one piece of information. Let's say someone wants to have a 10 dB directivity, for example, so you know your directivity is 100 dimensionless, and then you know your lambda, which is the frequency at which you're doing design, then AB is connected to the known piece of information. So that's one equation right here. But before going to other equation, let's talk about this 51% for a second. Now, the question that I have for you is that with open-ended waveguide, the aperture efficiency, if you remember the aperture efficiency of an open-ended waveguide, it was 81%. Now we are saying for horn antenna is 51%. Now this could be confusing in the beginning, because you might say, oh, a horn antenna, let me have an open-ended waveguide and horn. So this is my open-ended waveguide, this is my horn antenna. If you say, oh, the aperture of this is bigger, so it's more efficient, that's a wrong answer, because aperture efficiency has nothing to do with the aperture size. It has to do with how good you're using your aperture. Now, this is 81% for the reason that, as you see, part of the aperture has not been used in terms of field distribution. But this comes with an advantage, that these electric field here are all in phase on the aperture. They are all in phase. So because they're traveling through the waveguide, and they arrive in phase at the aperture. But with the case of horn antenna, as we discussed in the previous class, you see we have different distances to the aperture. For example, we could take R1 to the aperture, or we could take LH to arrive at the aperture. So when you have different distances to the aperture, when you arrive at the aperture, you're not completely in phase. So when you are not completely in phase, that's going to hurt you, and that's going to show in the aperture efficiency, which is 51%. So remember, you make your physical aperture bigger, because capital A times B definitely is greater than a small a times a small b. But the price that you pay would be on the aperture efficiency here. But overall, the expectation is you're going to still gain. For example, if you compare directivity of open-ended waveguide, which is 81% times a small AB, you expect that eventually this is going to be bigger than this. Therefore, you're going to get higher directivity. So that's something to keep in mind. Now, if you also want to go to see the expression of the aperture field, if you look at, for example, the field over the aperture of open-ended waveguide, we just write it as cos pi x a y hat. For example, I mean, you could have a constant here too, right? E naught cos pi x a. But now, if you write the same thing, and if you look at this, by the way, you see that there is a e to the power of j, for example, 0, which is 1. So this is phase. So you see, the phase of all of them are essentially the same thing. I mean, here I have a 0 here just to say, because you could have any reference for phase. But the point here is that you don't see e to the power of j a function. But if you write the electric field for the horn antenna, the field on the aperture could have a structure like this. I mean, this x and this x could be different, because now we are having the coordinates right here. But just as an example, then you get to the power, for example, j, something like that. So you see here, now this is your electric field over the aperture. Now, if you look at the electric field over the aperture, you see that at any x and y on the aperture, you get e to the power of j something. And that's essentially your phase term. That's essentially your phase term. So that shows that if you move from this point to, let's say, this point, the phase can change. But this change shouldn't be too much. Otherwise, it's gonna bring the aperture efficiency below. So that's something to keep in mind, and that's the reason that you go from 81% to 51% in this case. So that's to just give you an idea of why we go from 81% to 51%. So now this is one equation that we have. Now you might say, okay, what is the other equation that we might have? The other equation that we might have, I mean, could be just based on the geometry of this, because you can clearly see here that based on the geometry, I need to have LH to the power of 2 equal to R1 square plus half of A square. So remember, this is A divided by 2. So if you are in this triangle, so you would clearly have LH square equal to R1 square plus A divided by 2 square. So this is coming purely from geometry. Another equation that comes purely from geometry would be a similar equation for this triangle here. So then you can write LE square is going to be equal to R2 square plus B divided by 2 square. So that's another equation that we have. So far, we have 3 equations. Now, is there any other equation that's purely based on geometry? So the other equations that purely based on geometry, for example, could come from similarity of triangles. Remember, if you have a triangle like this, A, B, C, and then you have a parallel line to the base here, let's call it B prime, C prime. If you have that, and the reason I'm talking about that, think of this line and this line. So RH and R1, they're parallel to each other. It's similar to this. If you remember, then we say the triangle A, B prime, C prime is similar to triangle ABC. So if that's the case, these two triangles are similar, and as a result, I can write that B prime, C prime divided by BC is going to be equal to AB prime divided by AB and AC prime divided by AC. That's the result of similarity between the two triangles. So this B prime C prime divided by BC, AB prime divided by AB, AC prime divided by AC. Now, we have exactly the same situation here. Replace B prime C prime by RH and replace BC by R1. Similarly here, RE in parallel with R2. So I'm talking about these triangles now. So from here to here to here, this is my triangle, and similarly the same triangle here from here to here to here. So then you have two parallel lines, the same as that. So based on that, I can now write that RH divided by R1, RH divided by R1, the same thing as this divided by that, is going to be equal to this divided by this. So again, this divided by this. So now what is this? This part is A minus A divided by 2. Because remember, this is A divided by 2. So this thing is A divided by 2. And therefore, this would be A minus a small a divided by 2. And I think to see that, you may want to associate this with a small a divided by 2. So the whole thing is A, capital A divided by 2 minus A divided by 2, you get to here. So then I said RH divided by R1 is going to be A minus A divided by 2 divided by this, which is A divided by 2. And then you can just cancel 2, and then you get A minus A divided by A. That's going to be another equation that you have based on the similarity. And now you can go to this triangle here and have the same situation, you would say RE divided by R2, RE divided by R2 is going to be equal to, this is B minus a small b divided by 2 divided by the whole thing here, which is b divided by 2. So now you can cancel 2, and then you get, look at that, I'm just canceling 2, you get capital B minus B divided by B. So if you now go from, now if we just pause for a second here, this equation that we have comes from the antenna theory, of course. So this is the directivity that we desire. This is the aperture efficiency of the horn, and it connects the physical area to the desired directivity. This is known desired directivity. Then these 4 equations that we have are purely based on geometry. We didn't do anything EM here. This is based on geometry completely. Now, we have one more equation based on fabrication, because these are 2 cross-section. And if you want to put this as a 3D objects, then you definitely require that RE is going to be equal to RH. That's what you need to have the same RE and RH to be able to mechanically fabricate that. So the other equation that we have, which is RE equal RH, that comes from the fabrication aspect, that you have a 3-dimensional object. These two need to be consistent in the sense of RE equal RH, so that you can create a 3-dimensional structure from this. So that's something that comes not from geometry, it comes from the fabrication aspect, which of course is related to 3D geometry as well. So this is RE equal to RH. Now, how many equations we have? 1, 2, 3, 4, 5, 6. We had 8 unknowns here, so we need 2 more equations. Now, the 2 more equations comes from the idea of horns. You see, here the wave was traveling in phase, but then you wanted to expand the aperture, but then of course you're going to get some out of phaseness, because now you have different distances to travel. So you don't want to get too much out of phaseness. So in the previous lecture, I said if you have your horn, instead of like this, you flare it like that, then of course you get a bigger aperture, but then you get more out of phaseness, which is bad. So you wanna have a good balance between a large aperture and also not too much out of phaseness. So out of phaseness comes from the difference between R1, which is from this point is the fastest way to get to the aperture, and LH, which is the longest way to get that aperture. This is the shortest way, this is the longest way. So if they are too much different, you're gonna get lots of out of phaseness. If they are reasonably close, then they get that's gonna be acceptable to us. So we say LH minus R1 should be about something times lambda, because remember, everything is with respect to wavelength. So if you say LH minus R1 shouldn't be too much different, you're saying with respect to wavelength. So that's why I have wavelengths here. And the same thing here. So if you look at traveling here, at this point here, the shortest way to the aperture is R2, the longest way is LE. So they don't, if they are too much different, then of course you're going to get a bigger aperture, but then you're going to have lots of out of phases. You want to balance them. So you would say LE minus R2 should be something times lambda. So, and you expect that these two numbers that I'm going to write here, they shouldn't be too large. For example, you don't expect them to see 10 lambda, for example. Otherwise, it's going to be so much different. You want them to be reasonably close. So now the number for this is for H, one reasonable number is 0.375 lambda. This is this is a reasonable number for LH minus R1, and for LE is 0.25. So if you look at here, you see that it's not, I mean, LH and R1 are very close to each other. It's about 0.375 lambda, and for LE minus R2, they're even closer. So about quarter of a wavelength. So it's 1 divided by 4. So that's the type of out of phaseness that you can allow here. So both of them, as you see, are smaller than 1 wavelength, and both of them also are smaller than half a wavelength. So this is the two limits that can be acceptable, and these are coming from not having too much out of phaseness. So if I want to summarize, this is coming from, of course, antenna theory. This is also from antenna theory, keeping in mind that we don't want to have too much out of phaseness. This thing here comes from the fact that we need to fabricate this, and to be able to fabricate a 3D horn, we need RE to be equal to RH. And these fours are coming from geometry. Now, I have 1, 2, 3, 4, 5, 6, 7, 8 equations. So yeah, I have 8 equations, and 1, 2, 3, 4, 5, 6, 7, 8, 8 unknowns. 8 equations, 8 unknowns, and I can determine different aspects of my horn antenna based on this. Okay, I thought at this point, sometimes it's difficult to see that you need this for fabrication. I thought I'll just show it with the horn antenna. So this is the horn antenna that I have. And if you look at from this side, which is the wider side of the waveguide, you are here on this plane, you would be on the H plane. So if you look at this side for now, the distance from here all the way to the point that the waveguide starts. So from here to here, so from here to here, this is your RH. That's your RH. So from here again, go up to this point that the waveguide flaring start. So you have RH. Now, what is RE? RE, I need to rotate this 90 degree. Now we are on the narrower side of the waveguide like that. And RE goes from the aperture to the starting point of the waveguide. So you go from here to here. So this is your RE right now. So, and then your RH would be from the other side, from here to here. So as you see, this distance needs to be equal to this distance so that you can put them together and create your waveguide. So that's essentially the reason to have RE equal to RH. That's what we need essentially to be able to make our antenna. Okay, now let's consider an example for design. So the example that I'm gonna have would be, so I removed this, so let me just remove it completely and write my example. So the example says that we desire to have a directivity of 20 dB at the frequency of 10 gigahertz. So, and the purpose is to design a horn antenna, a pyramidal horn antenna to achieve this. So if we want to start this, we know that our pyramidal horn antenna starts from a rectangular waveguide. And if I look at this frequency belongs to X band. X band is approximately from 8 to 12. So this is almost the center frequency of X band. And I know that in X band, the waveguide is WR90. Then I'll go and I look at the size of the waveguide in WR90. And this is the size of the waveguide. And I know that a small a is 22.86 millimeter and B is 10.16 millimeter. So double check that. So this is the small a and B that we are supposed to have. directivity we also know is 20 dB, and you can get D in dimensionless. So we know that 20 dB is going to be 10 log 10 D in dimensionless. Therefore, D dimensionless is 100. So if it's 100, then it's also 20 dB. But here we're using dimensionless. So I'm going to use 100 here. So then I'm going to continue by saying D naught is 4 pi lambda square times 51% capital A, capital B. And lambda I also know because lambda is C divided by F, approximately 310 to the power of 8, 10, 10 to the power of 9, and that's going to be 3 centimeter, which is 0.03 meter. So that's our lambda that you can substitute here. And the rest you can just have write down all these equations to get the different dimensions of this of the horn antenna. For example, if I just look at the solution that I have here, then I end up with, so let me write this beside that. I end up with capital A to be 133.96 millimeter. So if you now look at that, you see we went from about 22 millimeter to 133 millimeter. Then with B, we went to capital B, which is about 104.82 millimeter. So you clearly see our aperture size increased. Although if we were using open-ended waveguide, the aperture efficiency was about 81%. With this, we are about 51%. So you see the aperture increase. And then the other thing that you, for example, can see if you solve the system is that your RE is going to be equal to 165.38 millimeter. And RH is also 165.38 millimeter. And this is actually a nice thing to look at because you clearly see RE is equal RH. So we enforce this to have 165. So we enforce this, and that makes sense. And other values are also here. For example, you can look at R1. So R1 is 199.41 millimeter, and I can compare this now to LH, which is 210.36 millimeter. Now, this is also interesting because you can actually see that the difference between R1 and LH is not too much. According to this equation, they should be relatively small. And if you look at that, you see the difference is in the order of 10 millimeter almost. So it's in the order of 10 millimeter and or approximately 1 centimeter. And if you look at my lambda was 3 centimeter. So it's in the order of lambda divided by 3 approximately. So, and I mean, I haven't made any exact calculation here, but you see, this is lambda 1 divided by almost 1 lambda divided by 3. So this number seems to make sense here. We haven't really exceeded much in this case, only about 10 millimeter and something, and some more, maybe 11 millimeter and something. So this is about R1 and LH. The other thing that's relevant to us is R2 and LE, which I get 183.14 millimeter and LE equal 190.49 millimeter. So if you also look at this, you see that they're relatively close to each other because you don't want to have too much out of phaseness. So in particular here, it's about 7 millimeter difference. Uh, so 7 millimeter difference. So my lambda is 3 centimeter. This is my lambda. So lambda divided by 4, 3 divided by 4, that should be 0.75. 3 divided by 4, so uh, so 0.75, which is close to 7 millimeters. So this is also seems to be okay. We're not too off. So the important thing is to realize that this R1 and LH are relatively close, R2 and LE are relatively close, RE and RH are the same thing, and you have increased your aperture size by these values. Okay, so let's finish this lecture with a couple of points, and then we try to wrap it up by the estimation of directivity. So one thing that I want to mention here is these two equations that we have right here, which is about these the differences between LH and R1 and LE and R2. So I want to get to this, and so let me perhaps remove this part. And so to understand this, you might have this question that why we have a stricter rule for LE and R2. And let me remind you that this is B and this is essentially our LE and this is essentially our R2. So this is our LE and R2, and then the other one is LH and R1, like that. So this is my LH, this is my R1, and this is my A here. So to understand the reason why we have a stricter rule on LE and R2, we need to pay attention to the amplitude distribution. So if you look at the waveguide, which is the starting point of the horn antenna, you see a cosine taper. But if you look at this cosine taper, it's present along this A. So this one is actually experiencing the cosine taper. So perhaps I can just plot it like that. So you see this one has cosine taper, but along B, it's uniform. We don't have any tapering effect here. So this tapering effect, because that's present along A or H plane, it enables us to have a less strict rule, because the problem with having a greater number here is that you become more out of phase. But remember, as you get to these edges, essentially, you have the amplitude taper. So this amplitude taper enables you to have a less strict rule. But in this case, you have a uniform distribution along B, and therefore we go with a more strict rule in this case. So that's essentially for us to understand why we have these two different rules from a conceptual point of view. Now this is aside. Let's talk about the half power beamwidths in the E plane and H plane for this antenna. So we have two approximate equations to estimate half power beamwidths. So half power beamwidths in the H plane can be approximated by 78 degrees lambda divided by A. So that would be the estimation of half power beamwidths in the H plane for us. For example, in the question that we studied, we had our capital A, we had our lambda, and we have 78 degree times that. So the answer would be in degrees. And in this particular example, that's going to be 17.47 degrees. So that would be our half power beamwidths in the H plane. Now, if we go to half power beamwidths in the E plane, we get to about 54 degrees lambda divided by B. And we have our B right here. We also know the wavelengths of operation, so we can calculate this, and this would be 15.45 degrees. So that would be 15.45 degrees. Now, based on this, we have two estimates of half power beamwidth. We also learned in the course that if you know your half power beamwidth in the two principal cut, in this case are E plane and H plane, then you can estimate directivity. And we also saw that there are a couple of equations to estimate directivity. One of them that you already saw in the videos related to measurement is the following. So this is, you estimate directivity by about 26,000 divided by half power beamwidth in the E plane multiplied by half power beamwidth in the H plane. And in these two equations, these half power beamwidths are in degrees. So this is our 26,000 divided by half power beamwidth E plane, half power beamwidth H plane. And if you get these two and you plug them here, you're gonna get to 26,000 divided by 269.91, which is the result of these two multiplication, and the final answer would be 96.33. That's the estimate of directivity for this case. And now, does this estimate make sense? It actually makes sense, because if you remember, we designed this horn antenna to have the directivity of 20 dB. So that was our directivity that we designed it, and then we found our parameters and everything, and we for the directivity of 20 dB, dimensionless directed 20 dB is 100. And now, based on this estimate, based on half power beamwidth, we got to 96, which is very close to the 100. So you see that this is this makes sense in this case. So that would be something, that would be one way to estimate the directivity, and you see that it actually it's close to the expected directivity for this design. One final note regarding this directivity equation is that there are other equations for directivity. For example, you might see this equation for directivity, which is directivity, maximum directivity is 41 to 53 half power beamwidths in E plane and half power beamwidths in H plane in terms of degrees. So this is another equation, and as you see, I mean, this is 26,000, this is 41,000. So you see that this is a different equation. This is more accurate for less directive antennas. For example, in the case of half a wavelength dipole antenna, if you'd like to use this type of equations, you could say that my half power beamwidth for a half a wavelength dipole antenna in the E plane is 78 degrees, but in the H plane, as you see, it's omnidirectional. Now, because it's omnidirectional in the H plane, you may say half power beamwidth in the H plane is 360 degrees. And now, if we apply this equation to this antenna, which is not directive, I mean, not a directive antenna, is, I mean, it's very moderate in terms of directivity. You just put these here, and then the final result become 1.47. So that becomes 1.47 estimate for the directivity of half a wavelength dipole antenna, and we know that the true value is 1.64. So if you compare this estimate to 1.64, you see that this equation does a better job. And if you do this equation, then you might have some issues. I mean, but sometimes you may use this equation, and instead of 360, you use 180, and then that's a different story. But if you want to use half power beamwidth 360, then this equation is better. But in general, you need to be very careful when you are using this equation. But for horn antenna, this seems to be the reasonable one to use in case you want to do some estimate on the directivity. Thank you very much.